Now we have all the tools we need to apply Laplace transform to problems arising in engineering, such as solving electric circuits. And not a simple one, but with rapid changes. Let's briefly recall what these properties are. So the first was the time shift theorem, where you took a function and shifted it by an amount a in time and multiplied by the unit step function. And the result was a Laplace transform of that function with the exponential. We also seen an S-shift, where you took a function multiplied by exponential and result was just shifted Laplace transform. And we have seen a time scaling, where you can take Laplace transform of a scaled argument, which is the same as just dividing a Laplace transform of that function by this factor, and also using the scaled argument of that Laplace transform. And we have seen linearity, where you can combine two functions and get a combination of corresponding Laplace transforms of these functions with the constant factors in front of them. So that's 4 properties of Laplace transform, and that's all you need to know to use Laplace transform to solve differential equations. And just a reminder, u is a unit step function, which is also sometimes denoted as the Heaviside step function by letter capital H, and it's 0 then t is less than a and 1 otherwise. So here is the first not simple example. Let's try and solve an ODE where the right hand side has a jump shifted to time t equals to 1. And let's assume that at time 0 the function was 0. Please follow me as I work it out for you. So first, as always, we use 3 steps. Step 1. Apply Laplace transform to the left-hand side and right-hand side. So if we apply it to the left-hand side, we get s times the function, because it's a derivative minus the value of this function is 0, plus 4 times Laplace transform of that function. And on the right hand side we get an exponential over s. That's from tables. Then we use the initial condition to eliminate that constant, and we have s plus 4 times f bar of s equals exponential over s. So that completes step 1. And now we just need to express that function as a function of s. So step 2, let's just divide the left hand side and right hand side by s plus 4, and we get f bar of s is exponential divided by s times s plus 4. Or we can use the partial fractions to write it as exponential over 4s minus exponential over 4s plus 4. And you can check it for yourself. And then there is one more step remaining, which is to invert that function, to find inverse Laplace transform of that function, and this will give us the solution. So just again, that was using the partial fractions, and now we're going to try and invert that function. So we have f bar of s, which is exponential minus s over 4s minus exponential over 4s plus 4. And if we apply an inverse Laplace transform to the first part, we can just use the tables. And from the table, we just see that this is 1 over 4 times shifted unit step function. So that's just a table. But the second expression is slightly more tricky. So you want to find a Laplace transform of an exponential over 4s plus 4. And that is not in the table. What do you think we should do here? I suspect you all guessed that that looks like something to do with the time delay, or rather inverse time delay. And that is the right guess. If you don't remember what is time delay or time shift, please watch previous videos. So we can write that as some other function, let's call it g bar of s times an exponential, the same exponential, and that is by time delay, inverse time delay, will give us a shifted version. So this is, by the way, you can take a factor of 1 over 4 outside, for example, just for simplicity. So this will be 1 over 4 g t minus 1 times a unit step function. So if you look here, what we called g was, by comparison, was just 1 over s plus 4. So that was the inverse time shift theorem. And all that remains for us to do is to find what this function g, original function, not the Laplace transform, was. And that we can use from table. So from tables, we know that the inverse Laplace transform of 1 over s plus 4 is, yes, that's right, it's exponential to the power of minus 4t. And if we substitute, so that is exactly is the g of t in this case. And if we substitute that inside the inverse Laplace time-shifted theorem, we will get finally the answer that inverse Laplace transform of that expression is 1/4 exponential to the power of -4 t minus 1 times unit step function shifted by the same amount. So that was the shifted argument, and we applied it to the inside of an exponential. And that allows us to write the whole answer as the original solution to this differential equation is a combination of the first part inverted, which was 1/4 u t minus 1, and the second part, which was 1/4 exponential to the power of -4 t minus 1 times a unit step function. Or you can simplify it and write the solution as 1/4 1 minus exponential to the power of -4 t minus 1 times a unit step function. So here you just applied an inverse time shift theorem to find that solution. So that is the answer, but it will be even nice if we can graph that, if we can plot the answer, and let's just do that. So let's look what it actually appears to be if you plot it against time. So f of t. So it was not existent before time 1, say 1 second. So that was 0 before that. And then you can see that it's starting to rise until it reaches steady state. So the steady state is given by 1/4, and then it's rising until it reaches that steady state. So that is what you can see here. That is a solution to rather non-trivial differential equation, which will be difficult to solve using previous tools which you learned in previous course units, but equipped with Laplace transform, you are now in a position to solve this equation.